Let's talk a little bit about how frequency combs work, okay? I like this picture. This is from Marco Lonchar's group at Harvard. It's actually a good picture. It's a frequency comb, right? Lots of colors, comb your hair with it. Very funny thing, you could do it right now if you're bored of listening to me, is you could Google laser comb. See what's the #1 hit. Someone should do it. Student, it's an assignment. See if you Google laser comb, see if Hair Max is still the top hit. Someone needs to, was Hair Max #1? You got to Google laser comb, not laser frequency comb. Anyway, it's a therapeutic comb. There's little LED lights on there. You can comb your hair every day. It gives you bigger, better hair, whatever. The science of hair growth. And the best thing is, like, I did that like in 2000, and the company still exists. So they were born about the same time as the laser frequency comb. I don't know if it helped them, the marketing or whatever. Anyway, that's not a laser frequency comb. Okay, I showed you this already, this array of optical frequencies. That's this magical, this special equation that describes the average frequency, okay? It might not, the frequency might deviate a little bit in some cases, but on average, this equation holds. It's a train of, near identical pulses, and I chose the words kind of carefully there, is you could have every pulse be the same, okay? These would be identical pulses, and those pulses come, just to remind you, at the inverse of this mode spacing. So you can think, of my handbell picture, right? If you just took two of these tones, ding, ding, dinged them together, you're going to get a beat frequency at the difference between them, right? That beat frequency is the rate at which these pulses come. You got lots of teeth here. They're all dinging together. That beat gets sharper and sharper and sharper. This is what Fourier tells us. We get a broader spectrum. If all of these tones are in phase, then this beat becomes very sharp. It becomes a super short pulse, just a few cycles of light there. I drew it here as near identical. The very important thing I pointed out before was this coherence. As I'll show you in a subsequent slide, the carrier, these oscillations, they're continuous from one pulse to the next. Okay, that's the coherent piece. The pulses don't have to be identical, and in fact, they aren't generally. And in fact, this is a simplification. It's only a handful of lasers that make pulses like this. But here in this case, we have the pulse group velocity is different than the phase velocity. So you get this carrier envelope phase slip. And so from one pulse to the next, the envelope has delayed with respect to the carrier. So there's some advance of the carrier. And that's this slip from pulse to pulse. And if it's coherent, then it's predictable. You get one quanta of it here, one delta phi, two delta phis. And this relates back, as I explained the other day, to those two key elements of the comb equation. So, okay, I talked about gears. Maybe we don't, I guess this is, this is PDF. These gears would rotate. I don't think we need to talk more about gears, but I wanted to come to this picture, which is kind of a fun way to think of how the comb works. So I said that frequency combs were used to count optical cycles. So how does that actually work? Let's imagine we had CW, continuous wave laser. It's a laser that's just continuously putting out a sine wave, okay? This laser, it puts kind of a continuous sine wave. It's not as good as the best lasers, but yeah, that's if you had ultra fast eyeballs, you would see sine waves like that, okay? And the sine wave has a period t. That was the 2 femtosecond number from the test earlier. The Fourier transform is a single frequency, right? Take a sine wave, Fourier transform, it's a delta function. what happened, or what would happen if we had an ultra-fast modulator, okay, and we could, a gate, if you will, and this gate has kind of an interesting Gaussian-like envelope, but we could turn the pulses on and off so that at exactly 10 cycles per pulse, okay? Pulse on, wait 10 cycles, or pulse on, 10 cycles, pulse on again, 10 cycles, pulse on again, just like I drew here. Then we could say that the time between these two pulses is exactly an integer related to an integer of the period. The spectrum starts to look like a comb. It's not just one frequency anymore. It's not just two. It starts to be many frequencies because these pulses are short. So Fourier tells us that if the pulses are short, then this comb spectrum has to grow bigger. But the interesting thing is this is a perfect divider. You see exactly there is that the nth frequency, the frequency of our light, is just an integer times the mode spacing. So actually, if lasers worked like that, the problem would have been solved in the 1960s. If you had a laser, and there were mode lock lasers that were developed in the 1960s, it would have been a perfect divider, and game would have been done. Okay? The problem is it's not the way lasers work. Okay? And that's because lasers are generated not in a vacuum, but they're generated in media where there's dispersion. And so you end up with this situation where the envelope and the phase slip with respect to each other. Sorry, I need this slide. So here you see again this change in the phase, okay? So you're like, it's over, you know? We're screwed. Now we got this thing slipping. How the heck are we ever going to measure that? This tiny little shift, ultra fast pulses, there's just looking for a little shift in the envelope relative to the phase. There's a simple math, though, is that shift is related to that offset, the shift of the comb. Yeah.
You said this is an issue because you're in a medium with dispersion.
Yeah.
Dig into that a little bit. It's not, yeah.
Well, it's because like the techniques that we use to make these lasers, this is the output of a mode lock laser. It happens in an optical cavity. Even if there was, let's imagine you sucked all the air out, you probably still have a crystal or a piece of fiber that the light is going through. And when it passes through that fiber or that piece of crystal, the phase goes a little faster than the envelope. And so you get this carrier envelope phase shift. So this seems like a big problem because now well, we have this tiny little phase shift here. It shifts all the comb lines by this ratio here. It's kind of in the math a little bit. It was actually clearer on my earlier slide. This one, you see it's the ratio of offset frequency to the repetition rate determines this shift. Yeah.
From the drawing at the bottom, it looks like the period between the envelope is a bit longer than 10 times t, right?
Yeah, my picture isn't perfect. This guy has good eyes. So he must be a professor from somewhere where only students can ask questions. Yeah. Yeah, actually you're right. The period seems to change there a little bit. The more correct way, if I drew this picture, is that the comb teeth would spread out such that as you extrapolate back to zero, you would not. It would be more of a fan out like that. Yeah, I drew it this way just for simplicity. So my drawing is a little bit wrong, and it still got published in Science. Referee didn't catch it. So, yeah. Okay, so we have this dilemma, is that now all of the comb teeth are shifted a little bit. How are we going to measure that? Well, the good news is that this tiny little carrier envelope phase shift, it shows up as a frequency shift. Okay, so what we're going to end up doing is measuring that shift in the frequency domain. And that's this very important process called self-referencing. So this is a very key element of optical frequency combs is to try to measure this small shift, the offset frequency. You see that you still have your harmonic relationship of the comb, but now we've added this offset frequency. So this was like the breakthrough piece, was to be able to generate spectra that were broad enough, an octave, we say, they have frequency F and 2F in it, so that you could take light from one side of the comb, nonlinear optics again, 2 times. Nonlinear optics is spectacular. That's why people like myself, you get addicted to nonlinear optics. It's like the most beautiful thing. You send in infrared light, out comes blue light or visible light. We then mix that with light from the blue side of the comb, and you see that the math is very simple. We get a factor of everything here gets multiplied by 2. Here, we just have the 2 multiplying the first term, the n value here, n, and here at the octave, it's 2n, the counting integer. So when we heterodyne these 2 tones together, we get this offset frequency directly. So that was a really important realization in the mid to late 90s. And I think it was first written, Thomas Udom, he first wrote it in his PhD thesis. He told me he made a mistake. He's a really great guy if you ever get a chance to meet him. He said he made a mistake. He wrote his PhD thesis in German instead of English. But you can read the math. Okay, more nonlinear optics, right? And this was really transformational. So when I was in Jan's lab, we were starting to work with the frequency combs. He came back from Germany. He said, hey, Hench is doing this. This is going to change things. Let's get to work, guys. So we started working, but then we didn't have anything to make an octave. And we went to a conference. Like, this is a great lesson. Went to a conference, and this guy, Janendra Ranka, stood up at the post-deadline session at Clio in 1999. He goes, hey, world, look what I found. You take a piece of fiber, you make some holes around the core, you can shift the dispersion, you can confine the light really tightly, and you just send in run-of-the-mill pulses from a femtosecond laser, and out comes white light. Boom, octave span. And we all went up and we said, we need a piece of that fiber. And it took a little while. The lawyers had to get involved because they were at, in those days, side story, Lucent, it's like, yeah, we got to relive the glory days of Bell Labs. They were on the stock market. Maybe it was about the time of this unfortunate incident, this guy Henrik Schoen, who was faking results. And they're like, no, we got really good stuff. We're the Bell Labs. I don't know, maybe they thought they were going to make money off of this. I don't think they ever made any money off microstructured fiber. But this is spectacular, and there's people in this room who now know and make devices like this, photonic crystal fibers. Philip Russell was one of the pioneers of this field. The key element is and maybe if you haven't seen this before, this is the diameter of a hair, about 100 microns in diameter. And in the center of that is this little honeycomb-shaped structure. And in that honeycomb is air holes that go the whole length of the fiber. Okay, they aren't filled up. They stay. It was like a straw. I don't think you could blow through it. It's too small, but it's like a straw. And then in the center, there's a tiny little core. And by constructing this arrangement of air holes, you can shift the dispersion away from the bulk zero crossing of silica, occurs about 1.3 microns, down to where its zero dispersion is around 800 nanometers, where these titanium sapphire lasers existed. So then when you launch a pulse in there, it doesn't immediately spread out. It stays localized, drives the nonlinearity, and gives you this kind of a spectrum. That was revolutionary, and those were, I put it in quotes, the seriously nonlinear fiber. That's what Jan Hall liked to call it. A little bit of history. That was from my notebook. October 6, 1999. This was like an anti-Murphy's Law experiment. I never had anything work so well before, but we went to the conference at Clio. It was May 1999. It took us until about October of 1999 to get the fiber, and in like 2 or 3 days, we had the first self-reference beat. And these were kind of our pictures from the lab notebook. David Jones, he's now a professor at University of UBC in Vancouver, University of British Columbia. We could make input pulse, we could make octave spanning, spectra. We made a very simple interferometer. We just took the light, we went through 10 centimeters of fiber. These are my pictures for lenses. We recollimated it, we put it in a nonlinear crystal to do this second harmonic generation. We put a filter, bandpass filter, 600 nanometers, and a detector, and that's what we saw. So I think that was, I believe, the first time those beats were seen, and that wasn't too long after that. We could control them, we could start to make clocks, we could control that whole gear work. Yeah, maybe in the sake of time, I'll skip over this. We could also examine the time domain properties, that carrier envelope slip. We measured that. It was later that they were all at the Max Planck. Hensch and Krauss teamed up. This was like the Nobel Prize winning work of Ferenc Krauss from just a couple of years ago on controlling attosecond properties in atoms by controlling that carrier envelope phase. It's really spectacular work. They followed on with that just a few years later. Let me say just a couple words about how you control the comb, because I told you these wheels are spinning. How do we enmesh the gears? Okay, so if we want to control the mode spacing, there's 2 ways to do that. One way is just to detect the rate at which the pulses come out of the laser. Okay, and we build a control loop, a servo control loop. We feed back to the laser cavity, and we change the length of the cavity because that repetition rate is related to how long the pulses go around in the cavity. And we control that length to match its frequency to match that of, say, a microwave reference. Okay, so that's one way to do it. The other way is a better way, and that is because optical lasers are now much more stable, much more low noise than any microwave. So in this case, we would take, the second approach would be to take a very stable laser. This would be like a continuous wave laser that is stabilized to a high finesse optical cavity, makes kind of Hertz level optical line widths. We can measure a heterodyne beat between one tooth of the comb and that laser, and we use that beat to control the mode spacing. It's kind of like an accordion door, you could think of. If you take a rubber band, another picture is if you take a rubber band and you lay it next to a ruler and you draw ticks on the rubber band at every centimeter, and then you stretch the rubber band, it stretches out like an accordion door. The spacing between each tick gets longer, but if you go to the nth tick, it's n times the spacing now. So we can pick a comb tooth in the optical domain, stretch it out, shorten it a little bit, its frequency, lock it to a very stable CW laser, and now you just take that same equation and you rearrange it, and we get that the repetition rate is the optical frequency plus a few small microwave tones divided by n. The advantage of doing it this way is that optical signals are now super stable. The fractional stability is 3-4 orders of magnitude better than the very best microwave. This is a bit of a technical detail, but this is actually why optical clocks are so good. We've tested that. I already told you that the comb works really well. The only way to test it, it's so good, is you have to build 2 combs and compare them against each other.